Hey guys. This is Space Train, your daily express till the edge of the space, and today we will talk about what is a string theory. Grab your tickets and let's go. Don't forget to subscribe to get unlimited pass on our expedition. We live in a wonderfully complex universe, and we are curious about it by nature. Time and again we have wondered, why are we here? Where did we and the world come from? What is the world made of? It is our privilege to live in a time when enormous progress has been made towards finding some of the answers. String theory is our most recent attempt to answer the last, and part of the second, question. String theory. In particle physics, a theory that attempts to merge quantum mechanics with Albert Einstein's general theory of relativity. The name string theory comes from the modeling of subatomic particles as tiny one-dimensional string-like entities, rather than the more conventional approach in which they are modeled as zero-dimensional point particles. The theory envisions that a string undergoing a particular mode of vibration corresponds to a particle with definite properties such as mass and charge. In the 1980s, physicists realized that string theory had the potential to incorporate all four of nature's forces: gravity, electromagnetism, strong force, and weak force, and all types of matter in a single quantum mechanical framework, suggesting that it might be the long-sought unified field theory. While string theory is still a vibrant area of research that is undergoing rapid development, it remains primarily a mathematical construct because it has yet to make contact with experimental observations. In 1905, Einstein unified space and time with his special theory of relativity, showing that motion through space affects the passage of time. In 1915, Einstein further unified space, time, and gravitation with his general theory of relativity, showing that warps and curves in space and time are responsible for the force of gravity. These were monumental achievements, but Einstein dreamed of an even grander unification. He envisioned one powerful framework that would account for space, time, and all of nature's forces, something he called a unified theory. For the last 3 decades of his life, Einstein relentlessly pursued this vision. Although from time to time rumors spread that he had succeeded, closer scrutiny always dashed such hopes. Most of Einstein's contemporaries considered the search for a unified theory to be a hopeless, if not misguided, quest. In contrast, the primary concern of theoretical physicists from the 1920s onward was quantum mechanics, the emerging framework for describing atomic and subatomic processes. Particles at these scales have such tiny masses that gravity is essentially irrelevant in their interactions, and so for decades quantum mechanical calculations generally ignored general relativistic effects. Instead, by the late 1960s the focus was on a different force, the strong force, which binds together the protons and neutrons within atomic nuclei. Gabriele Veneziano, a young theorist working at the European Organization for Nuclear Research, CERN, contributed a key breakthrough in 1968 with his realization that a 200-year-old formula, the Euler beta function, was capable of explaining much of the data on the strong force then being collected at various particle accelerators around the world. A few years later, 3 physicists, Leonard Susskind of Stanford University, Holger Nielsen of the Niels Bohr Institute, and Michiru Nambu of the University of Chicago, significantly amplified Veneziano's insight by showing that the mathematics underlying his proposal described the vibrational motion of minuscule filaments of energy that resemble tiny strands of string, inspiring the name string theory. Roughly speaking, the theory suggested that the strong force amounted to strings tethering together particles attached to the string's endpoints. String theory was an intuitively attractive proposal, but by the mid-1970s more refined measurements of the strong force had deviated from its predictions, leading most researchers to conclude that string theory had no relevance to the physical universe, no matter how elegant the mathematical theory. Nevertheless, a small number of physicists continued to pursue string theory. In 1974, John Schwartz of the California Institute of Technology, and Joel Skirk of the École Normale Supérieure, independently, Tomoaki Yoni of Hokkaido University, came to a radical conclusion. They suggested that one of the supposedly failed predictions of string theory, the existence of a particular massless particle that no experiment studying the strong force had ever encountered, was actually evidence of the very unification Einstein had anticipated. Although no one had succeeded in merging general relativity and quantum mechanics, preliminary work had established that such a union would require precisely the massless particle predicted by string theory. A few physicists argued that string theory, by having this particle built into its fundamental structure, had united the laws of the large, general relativity, and the laws of the small, quantum mechanics. Rather than merely being a description of the strong force, these physicists contended, string theory required reinterpretation as a critical step toward Einstein's unified theory. The announcement was universally ignored. String theory had already failed in its first incarnation as a description of the strong force, and many felt it was unlikely that it would now prevail as the solution to an even more difficult problem. This view was bolstered by string theory's suffering from its own theoretical problems. For one, some of its equations showed signs of being inconsistent. For another, the mathematics of the theory demanded the universe have not just the 3 spatial dimensions of common experience but 6 others, for a total of 9 spatial dimensions, or a total of 10 space-time dimensions. We will talk about dimensions and more development of string theory in our next video. Stay with us, and don't forget to comment, what do you think, is the string theory ultimate theory of everything, or just a waste of time? There are lots of questions left, so don't space out, and leave some space in your brain for answers. I hope you enjoyed this video. If you want to see more, subscribe and click the bell button, to get notifications on our latest videos. If you are still here, grab your knowledge and get out of my train.